Hello, today I want to introduce the concept of complex eigenvalues, and to do that I want to start with this computation here. I want to calculate the characteristic polynomial of this 2 by 2 matrix. Some of you know that this corresponds to a rotation matrix. So just from the geometry itself, it cannot have real eigenvalues, right, as they represent elongations along a direction. Um, let's see. Let me calculate the following. For that, let's find the determinant of this associated matrix. Cosine of theta minus t sine theta negative sine theta cosine of theta minus t. And well, the corresponding difference of diagonals. So this is cosine theta minus t squared plus sine squared theta. Well, let's see. For this case, I expand it, so cosine squared theta minus 2 cosine theta t plus t squared plus sine squared. Well, combining these two into the known trigonometric identity and then rearranging the terms, I can write it as t squared minus 2 cosine theta t plus 1. Well, what do we know from here? Well, then the roots are given by the quadratic formula. So I'm going to call them lambda as usual, right, for eigenvalues. This would be, well, negative of the linear coefficient, so 2 cosine theta plus or minus the square of the linear coefficient, so 4 cosine squared theta minus 4 times the quadratic coefficient times the constant coefficient, so minus 4, and all over the following expression, which corresponds to 2. Now, expanding on this, I have that this is cosine theta. Since I can factor a 4 from this expression, it becomes a 2 out of the square root sign. So since I have this dividing and I will have a 2 and a 2 here, I can cancel. So this becomes plus or minus cosine squared minus 1. Oh, but this is known. This also comes from the trigonometric identity, and I can identify this as negative sine squared. So I'll write this as cosine of theta plus or minus the square root of negative sine squared theta. Now, just to be safe, I'm going to write it in the following way. Cosine plus or minus I, absolute value of sine. But well, we don't really have to write it in this particular way. I may just write it like this. It's not bad to be safe. You know why? If I have that sine of theta is positive, well, I will have the plus minus I here. If I have sine to be negative, I will have minus plus in this situation. So it still account for the two eigenvalues associated here. So I will have plus minus I sine of theta, either way. So one important remark of what we have here is that the associated eigenvalues of a matrix with real entries, if it turns out to be complex, it comes in pairs, and as we'll see later in the theorem. As you can see here, if I'm going to call lambda 1 to be cosine of theta